So, I sort of made a computer. Now, I already sort of recorded a video right after I finished the computer that I hope goes through most things, so I'm not going to take too much time here at this sort of, not exactly intro, but overview, I'll call it. So, the computer started off like this. This is actually what was sort of left after I tore down a previous computer. That previous computer, yeah, I think I mentioned it in that video that I already recorded, so I'm not going to cover it too much, but yeah, so the light blue that you can see is the ALU. The darker blue on top, that's a sort of thing called a bus. It sort of just sends information around. Oh, and I totally forgot about this. You can see on the bottom that you can sort of see those are repeaters. That's a two-way repeater. I didn't end up using those at all in my final computer 2.0, because by the way, this is my computer 2.0, because I've also made a computer 1.0, a 1.5, and a 1.6, mostly. Whatever. I'm not going to make videos on them. They're old anyway, and I promise this one's way better. Seriously, it's great. Anyway, you can also see that little multicolored board. That thing was what I initially used to plan out the computer before I even started building anything on top of what I already had. I think this sort of just shows what I started with a little bit better, but yeah. From here, I didn't really take many screenshots in between, so we're gonna jump straight to here. Yeah. You can see, as the diagram says from previous, yeah, the purple bit is still there. There's just a lot more stuff on top of everything. Actually, this is pretty close to its completion. So, just rotate it so that then you can see the next step. This turned into this. Yeah. Maybe this looks like a bigger change to you, but actually this was like, when you think about it, okay, those two long parts look really repetitive. Huh. I wonder how many uses of /clone it took. Because, yeah, no way would I build all that by hand. Maybe one day I'll build it in survival. That would be fun. But until then, no. That's just use of /clone. Not too big of a change. From there, it grew slightly more to this. I just sort of added an output display, as you can see here. And I just decided to color it brown to blend in with the unpowered redstone lamps. You can sort of see it just maybe looks slightly better. So basically, it makes literally any number look less like an 8, which is good. Anyway, from there, I'm just going to show you a video of the color coding. Although actually from the start, you can sort of see that board I mentioned. So you can sort of see it's covered in signs. Maybe I'll go over it. Oh, actually, I think I'll go over it in the 20 whatever minute video that I recorded as soon as I finished the computer, so yay. Anyway, here's the color code. Oh, and better yet, it's a color code video that happens to be about the same length as a song I made in Minecraft, so you get to listen to that too. So that's it. Well, for me, present me. Because as I've mentioned a little bit before, yeah, I actually recorded a video right after I finished it. I just didn't post it at all. So I suppose I finally get to use it. So I finally finished my computer. So I know this might look terrifying to at least some people, but if I break it down, it actually is ridiculously simple. It's just like an 8-bit computer, and, well, when it comes down to it, I mainly use maybe like 2 types of circuitry. My favorite design is literally just to have, horizontal lines, redstone torches, more horizontal lines, more redstone torches. So this is the program memory. This pink is the program memory. And basically whichever line is unpowered, those redstone torches are powered on. Then these are sent to this red, the program decoder, and then, well, I sort of ran out of colors. Not exactly, but I decided to use red for both the program decoder and anything that involves the program, like the program memory and program decoder, like doing something. That's also controlled by red. So I think these might be called control lines, whatever. So they're the things that the program actually uses to make stuff happen in the rest of the computer. Anyway, with the program decoder, I take it back, 3 types of circuitry. or maybe 2 with 2 subsets in one of them. There's sort of 2 subtypes, whatever. One that uses both repeaters and redstone torches, that it sort of just chooses one. With these inputs, every output is unique. Only one of these will be turned on at a time. Well, mostly. I could make it choose more, but they're more unique. With this, though, if any of these are on, the output is on. With this one, all of the outputs, or inputs rather, have to be a certain thing for the output to be a 1. Or in this case, I suppose 0, but whatever. 1, but signified by it being powered off. Anyway, with the program decoder, again, I just have lines of just redstone with redstone torches on the side. If I want, I should be more specific. If, in order to make this thing be active, I want this to be a 1, then I put a redstone torch. If this needs to be a 0 in order for this to be active, then I put a repeater. And there's more complicated ways to do that. As you can see, I usually put it off to the side, just because if there's 2 in a row, then I should just put it off to a side. So if you're thinking of like building a computer, that's a really good strategy. Or not just a computer, anything. And then redstone torches, again, to choose exactly which control lines will be activated. So these are sort of like the combinations for instructions here. I should be slightly more specific. These things control the opcodes. Each opcode, I suppose these could be considered micro instructions, but instead of having like a little mini clock with like extra clock cycles and sort of like one big clock cycle subdivided into micro instructions, they're basically like smaller instructions within a clock cycle. They're sort of all run in parallel though. So one opcode might have, the longest is probably only like 6 of these lines. Let me see. 1, 2, 3, 4, 5, 6. Yeah, 6, maybe 7, 8 at the most, maybe. Each opcode will only use like that many things to activate all the control lines it needs to. Just because you'd think I could get away with doing them all on the same thing, but no, because there might be an instruction that says, okay, if that particular bit is on, then turn on a particular bit in these control lines. So I couldn't really do it all at once. So this the program decoder ended up being bigger than I thought it would, but honestly, it's probably the most complicated part. But I mean, look at it. It's a waffle. It's just a gigantic waffle. There's like lines running. How I know it looks confusing, but don't worry about it. If you're planning to build a computer, seriously, just try. It's slightly less difficult than you're thinking it is. Of course, that's just the programming area. Can get more complicated with, well, I sort of color-coded things, so you can sort of guess that, okay, I see blue and a little bit of gray, cyan, orange, yellow, green, red, yellow again, and just white. And okay, so this area is more complicated. So down here this is probably, to most people might consider this the most important part. This is the ALU, the part that actually does math and whatnot, the part that can actually add things. I just looked up a design for it. I think this is from Nubosaurus. I can link it, but yeah. This thing, yeah, it's useful, but it's sort of expandable sideways though, so it's definitely complicated, but you can sort of copy it from the video and then just use /clone 1,000 times and it works. This might also look complicated, but this is literally just memory. I built it myself because there weren't any good designs for Bedrock, but I'll probably make a tutorial for it. It's dual read, meaning that each of these are just 4 registers. These are sort of like the most important parts of memory. I mean, like, this is memory 2, but none of that stuff can directly act as inputs to the ALU. So each of these has one, I suppose, write area from the bus, and then it can read to either the top or the higher or the lower input to the ALU. So they're controlled by these lines on this side. I think this adds up to 9 control lines. Yep. So there ended up being a lot of control lines. Oh, one thing I should note, if you ever plan on building a computer in Minecraft, plan ahead. Don't be too stupid. I think by the way, this computer world isn't the first computer I was trying to build in this world. I actually sort of tore everything down except the ALU, a little bit of the bus, and the registers, because in the older version, it was not good. See how there's, what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times 2, that's 22. 22 control lines. So each of my instructions for, like, the program would be 22 bits. That's sort of massive. And I actually finished the computer, mostly, except I never programmed it. I didn't even build the program memory area because it was not good. And I could tell that even before finishing it. Now, though, I sort of made opcodes, planned everything out beforehand on... this is going to take time to fly over. I planned everything out on this little board thing. It didn't end up being the final version whatsoever, but it was really good to write everything out in Science. So I basically had 8 basic instructions, and then, and 3 bits to choose which instruction to use. And then, well, what parameters I suppose you could call them. Inputs, whatever. For example, the jump branch command would sort of change where the program memory is, like what line of code you're reading from. It would jump to whatever is written out in these last 6 bits if the flag chosen there is set. Flags are sort of like, okay, was the last operation the ALU did, no, actually take it back. It wasn't the ALU. I just read from the bus to make it more generalized, more useful. So the last value on the bus, was it a 0? If yes, okay, good. Did the ALU... Was the ALU used last clock cycle, and did it set the carry flag? Did we try to add 2 numbers that were too big? And, okay, what else is there? Sign is the most significant bit of the ALU output set. Maybe it was No, maybe it was of the bus again, just to make it more generalized. That's basically so if I decide to use 2's complement, that's a thing that allows you to handle negative numbers. So that's why I called it a sign flag. And there's other commands here, but these are sort of out of date, I suppose, since this is the most up-to-date version. And I also went through like 4 versions of the opcodes before I find these are identical. That's interesting. I suppose that makes sense. Oops, whatever. I must have had one in my inventory and put one in the chest, but when the one in my inventory became outdated, I sort of just assumed it was a newer one. Whatever. So yeah, this one and the one that was in my hand are the newer ones. I can go through the opcodes later, but that's complicated. I'm sort of just going through the actual computer. Oh, and I mentioned this isn't the initial computer I built here. I was planning to use some map art for the user input just to make it look nicer, but haven't done that on this world yet. I might. I suppose the next part I should cover is the big flashy part, the output. Given how massive it is, it looks terrifying, but just a hint. Massive is generally not good, so it looks terrifying. But the reason it's massive is because I built it in like an hour. So I can definitely go over roughly how I did this relatively quickly. There's 4 inputs at the, I actually should back up, 7 segment display. That means there's 7 lines going in. I worked a little bit on making this front area compact, but basically then at the end I had, okay, 1 there, 1 there, 1 there, 1 there, and 1 there, 1 there, 1 there, and then I need to activate all of these with like redstone torches somehow. So like I could have the option to put a redstone torch there. So by default, this one is powered and the redstone torches are off, but if this one is selected, then its redstone torches are on to power it. Same deals with the program memory. Then I just use this little extra space because there's only 7, not 8, to send a signal down to the bottom. And yeah, basically I repeated that without these redstone torches 16 times, I think. 1 for each digit. And that could definitely be more efficient. But it works, so that's an important thing. And this stuff at the top is literally just saying, okay, if only this one is active, then this line is going to be the one that's off. If it's 0, 1, it's this one. If it's 1, 1, then it's this line. This is 0, 0, 1, 1, 0, 1, binary. You get it. It's literally just redstone repeaters and torches, and it's the most simple logic possible, just combinational logic. I suppose it's a fancy term, but basically wherever I need this to be a 1 in order for this to be off, I put a redstone torch. Wherever it needs to be a 0 for this to be the one that's selected, then I put a repeater. It's basically just that plus some knowledge of how binary works, and yeah, that's pretty much it. And then I repeated that a lot and then had to code in, okay, this is, I don't know, maybe it's an 8, so that means all of them need to have redstone torches, or it's a 7. So then I sort of did it by trial and error to figure out exactly which ones I needed to be active for each number, but and I only had to build one of them because, of course, /clone exists. Even easier. Great. Similarly, for this RAM, the RAM is gray. But I know this looks terrifying again, but seriously, I just had to build one of these things. Oh, and this is sort of a half dismantled version because I obviously don't need any write functionality. I literally just need to output it straight to the, 7-segment display. Here, though, it's a little bit more complicated. There's a little bit less space for me to try to wire up something that could let me read from the memory. and output it to this blue bus, but in the end it worked out. And if you actually take a look at it, it's relatively simple. It's just a little repeater that can power itself with 3 redstone dust, and a little bit of functionality with like sticky piston, lock. So the nice thing on Bedrock is, of course, that repeaters on the side of pistons or sticky pistons get powered when they are powered. So that works. That was really nice. And then, so basically, in order for, let's say this is a 1, so that's off. In order for this to be on, though, this has to be off, and this thing enabling right has to be off. And then that would turn to a 1, that would be powered, and, well, great. And if I'm reading, and it's a 1, then that's going to be off, and if I unpower this, this would be off, that would be on, so that means I would be reading the 1, or writing it from there to there, or reading it, whatever. It's sort of complicated. If you're reading from RAM, if like the register is reading from RAM, writing to a register, then I suppose you could also say from the perspective of the RAM, it's the one writing. But yeah. So then I just had to build one of these cells in a way that was tileable, and then massive amount of /clone. Best command ever. So similarly to how this thing, I feel like there's probably a word for what this sort of thing does. Decoder, I suppose. But specifically, this is a decoder that turns binary to, a unique output. So, okay, there's 6 inputs to the 6th power, 64. Okay, 64 outputs. Here, yeah, I think there's also 64 of these, including these 4 isolated over here. Of course, since these units are like twice as long as those, well, yeah, it's a good deal longer. Twice as long. Well, not exactly twice as long, since obviously those 4 are set off to the side, and I think about like 1 or 2 of the units start before the program memory block starts. So I think that's most of the sweeping stuff. Ooh, I forgot to mention the quote-unquote stack pointer. By stack pointer, I mean, okay, it's another register. It's exactly the same as all the other registers, except after I built a lot of other stuff, I added some other stuff on top. Great. I think you can sort of see what I built later than the other stuff just by, okay, what's on top. Like, okay, after the bus, of course, came a lot of anything that would be writing to the bus, like this green user input, or yellow, or the orange for flag. Oh, I forgot to mention the flags. I haven't really gone down to the bottom. But yeah, these, just like the RAM, I use the same sort of thing with, it's my favorite memory design, really. And then it can be enabled by this line here. It's triggered by the clock. So the registers sort of update every clock cycle. This is annoying me that it hasn't updated yet. Look at it, it's wrong. It hasn't updated yet, but whatever. Anyway, I suppose this area might also look slightly wire heavy. Again, you can see what I built later just because, okay, you know how I mentioned oh, geez, I just remembered these. I mentioned I like sort of like counted up these for like 22. No, I'm wrong. Because after I had those 22, I realized I needed a few other things. So, okay, 23 is over here. I know for a fact there's a 24 somewhere on the bottom over there. This one I suppose would qualify as a 25th. So, as things went on, it became slightly more complicated. Ooh, and this area was a mess too. So in order to choose what byte of RAM I'm going to read from, obviously the program has to have some say, so then there's sort of like a mesh between that cyan representing the decoder for addresses and RAM, and the red program stuff. Looks a little bit chaotic, or more than a little bit chaotic, since right on top of it, oh yeah, built later because it's on top. Great. And then this clock was built on top of that. Actually, this clock used to be even higher up, since, you know, if the sky is literally the limit, there's no reason to be compact. So then I tried to make the clock more compact afterwards. I think I probably have some screenshots of the earlier version where it looked slightly messier. Honestly, it hasn't gotten much better though. Anyway, program counter. This is not my design of program counter. It's really cool, and you can't see it because of everything around it. Oh, and this enables writing to the program counter for like branching and jumping from this area. Smart pistons. Another thing that I overuse. If you don't know how smart pistons work, they're amazing. Let me go find an example that won't break everything. I think the flag uses one. Where? It's over here. Yes. So if I power this, then that is extended down. But obviously now, well, okay, that's powering that, that's powering the block, that's powering the piston. So that piston is now trying to push up because that redstone block there, but it can't because the one on the top is extended. So then as soon as I release this, everything gets pushed up. Even though it isn't slime, it sort of kind of acts like slime. And in the sense that you can both extend and then retract it. It's as though it's a sticky piston in slime, but it has the benefit of you don't need to make everything surrounding it made out of terracotta. Looks a lot better. So then I use them here. Yeah, hint. I built the green stuff over here. Oh, I forgot to mention it. The green controls the ALU, sort of. See, you can sort of see how this blue ALU has things going into it. It sort of enables certain functions. And, well, yeah, that's actually one of the first things I built. Right after I built, like, the first maybe 4 bytes of RAM or something like that. But then afterwards I needed to thread through other stuff, so you can sort of guess that, like, anything involving a smart piston was probably added after the other stuff, just because smart pistons are so easy to send a signal down. Meanwhile, like this takes up 2 blocks instead of just 1. So wherever and smart pistons add a little bit of delay, so wherever possible, up until that point, I would tend to use just normal stuff, you know, normal staircases instead of weird redstone like smart pistons. It's useful though. Other than that, I don't know what I haven't covered yet. I should probably cover the clock briefly at least. Half of the complexity of this clock is because there's this one function that pauses the clock and waits for user input. It's not a perfect command. I think, like, I really just supposed to put a sign, confirm, and please wait. That please wait should be in bold rather than the confirm, but whatever. Because please wait, if you don't do that, there's nothing stopping you from sort of making the clock entirely on and not changing and sort of just staying like that forever. So that's bad. Whatever, though. It's not meant to be perfect. So then there's a little bit of circuitry to deal with pausing it and unpausing it, and then these droppers facing into each other. This system is sort of to make sure it doesn't get unpaused and then have the thing say, okay, oh yeah, we were on this line of code. I remember now, the clock is now active again. We were on this line of code, and oh, it says pause the clock. Because this sort of activates before the counter increments. Or rather, it activates at the same time as the thing increments, as the counter increments. So I really don't want to pause the clock as soon as I've, unpaused it. So initially I just had this one dropper thing with that leading directly into it, but then it sort of pulsed twice. So then I just added an extra little thing, and then a lot of delay because, okay, realistically, I'm probably not going to have two read from user inputs right next to each other. Yes, I will. Yes, I will regret this. Whatever. Especially since, by the way, the clock is 8 seconds long. I'm going to say that again. The clock is 8 seconds long. So in other words, if I want to have two user inputs right next to each other, I'm going to have to have a user input and just wait like 16 seconds for the next one instead of just because I might have to wait 2 clock cycles instead of just one. Whatever. It works. That's all that matters. So this was a little bit of a rambly video, but hopefully it explains some of what the computer does. And I haven't exactly explained what the computer does. The opcodes are slightly important, but that can be handled later. Bye.